Hello and welcome. We're really excited to have you with us today as we take a closer look at the fascinating world of steel leveling technology. Whether you're familiar with the process or this is new territory for you, our goal is to provide a clear and engaging breakdown of how modern techniques and innovations are improving the way we flatten and process steel. Throughout the presentation, we'll guide you through everything from the basic science of stress and strain to more advanced concepts like our independent drive system. We'll also dive into how traditional methods have evolved, why precise flatness matters more than ever, and how Delta Steel Technologies is pushing boundaries to deliver exceptional results. We're here to share practical insights, offer solutions, and show you the tangible benefits of implementing these advanced systems in your operations. Whether it's achieving the highest standards of flatness, reducing internal stresses, or increasing your overall production efficiency, we'll cover it all. So get comfortable and ready to explore the key advancements in steel leveling that could take your production process to the next level. Before we jump into the science behind leveling, let's take a moment to address a fundamental question. Why doesn't steel come perfectly flat straight from the mill? The truth is, it's not just one single issue, but rather a combination of factors that interact during the manufacturing process. The first factor is thermal. During production, we have uneven cooling patterns, where the edges cool at different rates than the center. Think of it like a cake that cracks when it cools too quickly. Our steel develops internal stresses from these temperature differences that lead to defects like warping, buckling, or wavy surfaces. Moving to mechanical factors, imagine the massive rolls used to flatten steel. These rolls actually flex under pressure. We call this deflection. They also wear down over time, creating subtle variations in the steel's surface. It's like trying to roll out dough with a rolling pin that's slightly worn in the middle. You'll never get perfectly even results. Additionally, during the recoiling process of the hot strip, we face significant tension-related challenges. As the hot steel is wound into a coil, tension variations occur between the inner and outer layers. The material closer to the core experiences different tension forces compared to the outer wraps. This inconsistent tension distribution creates localized stress patterns that can manifest as waves, ripples, or loose edges in the final product. The temperature variations during this recoiling process also contribute to these tension-related shape defects, as the steel is still cooling while being coiled. Think of it like wrapping a long ribbon around a tube. If you don't maintain perfectly even tension throughout the wrapping process, you'll end up with some areas tighter than others, creating permanent shape variations in the material. The third key factor is metallurgical. As the steel cools, its internal structure changes through phase transformations. These changes don't happen uniformly across the material. Additionally, the chemical elements in the steel aren't perfectly distributed, leading to variations in properties across the width and length. The bottom line is this. These three factors, thermal, mechanical, and metallurgical, are constantly interacting during production. It's this interaction that makes it theoretically impossible to produce perfectly flat steel straight from the mill without some form of post-processing like leveling. Understanding these fundamental limitations helps us better appreciate why leveling operations are such a crucial part of our steel processing workflow. Now that we know why steel isn't perfectly flat, let's explore how we can correct these imperfections and deliver a product that meets the highest standards of flatness and quality. The solution lies in a process called leveling, which is built around the concept of material deformation. In this context, deformation refers to altering the shape of the steel through compression, elongation, or a combination of both, depending on the method used. Leveling addresses internal stresses and shape defects by systematically bending, stretching, and compressing the steel. This controlled deformation redistributes and eliminates residual stresses, improves uniformity by equalizing thickness variations, and corrects inhomogeneities in the steel's microstructure, ensuring the material achieves stable and uniform flatness. It can even minimize the impact of internal defects, such as inclusions, by spreading them more evenly across the material. To understand how these deformations are created and controlled, we need to take a closer look at how steel behaves under force, which we will explore on the following slides. Let's jump right in. Before diving into the leveling process, it's essential to understand the stress-strain curve. This curve is the cornerstone of how we predict and control steel's behavior during leveling. Starting here is crucial because it provides the insights we need to control and predict how steel responds under force. The stress-strain curve is a valuable tool that demonstrates the relationship between two fundamental factors: stress, which is the force applied to the steel, and strain, which is the relative amount the steel stretches compared to its original length. Think of this curve as a roadmap that gives us critical information about the steel we are going to process. This curve can give us information like the exact point where the steel will start to permanently deform, how stiff or flexible the material is, which tells us how it will handle stress, the maximum force the steel can endure before it starts to fail, the transition point from temporary elastic to permanent plastic deformation. In the next slide, we'll explore this curve in more detail and break down each of these key factors so we can see exactly how they guide our leveling process. Let's start with the basics by looking at this graph of a typical stress-strain curve for steel. To make it easier to follow, we've highlighted three key areas on the graph using rectangles. Elastic zone, first rectangle in yellow. This is the initial straight-line portion of the curve. Here, the steel behaves elastically, meaning it will return to its original shape when the stress is removed. The slope of this line represents the Young's modulus, which is typically around 30 million pounds per square inch for most steels, indicating the stiffness of the material. Yield point, second rectangle in green. This is the point where the curve starts to bend or curve away from the straight line. At this stage, the steel reaches its yield strength, indicated in the orange circle, and any additional stress will cause permanent deformation. Up to this point, any strain, stretching, is temporary, meaning the steel can return to its original shape once the stress is removed. Beyond this point, the changes are permanent. Ultimate strength zone, third rectangle in blue. This section extends from just after the yield point to the ultimate strength. In this zone, the steel continues to deform plastically, meaning it won't return to its original shape even after the stress is removed. The ultimate strength represents the maximum stress the material can withstand before starting to weaken. While the steel is not yet fractured, it's been permanently altered and is under significant strain. To sum it up, in the elastic zone, the steel can stretch and return to its original shape, like gently pulling a rubber band. At the yield point, the steel starts to deform in a way that can't be reversed. It's like stretching that rubber band to the point where it doesn't fully snap back. The ultimate strength zone shows the maximum stress the steel can take before it begins to fail. The material is permanently changed here, but it hasn't yet reached the point of rupture. Understanding this curve is critical for processes like leveling and stretching, as it allows us to control the steel's behavior under stress and ensure it performs as required. Now let's take a closer look at how higher strength steels impact the stress-strain curve. The key concept here is that the strain or elongation needed to reach the yield point increases as the strength of the steel goes up. Here's how it breaks down. For 40,000 psi material, it only takes one yield strain, or 0.136% strain, to reach the yield point. With 80,000 psi steel, you need two yield strains, which equals 0.272% strain. For 160,000 psi steel, it requires three yield strains, or 0.544% strain to hit the yield point. As the strength of the steel increases, more strain is needed to cause permanent deformation. This means that higher strength steels need greater control and precision during processing to achieve the same level of flatness. Stronger materials require more elongation to get the job done, making the process more demanding. Delta Steel Technologies offers three main types of machines to make steel flat. This diverse range of solutions makes Delta product agnostic, meaning we focus on solving problems with the right tool rather than pushing a single product. Our approach begins with understanding the specific markets our customers intend to serve. By analyzing their application goals, production requirements, and budget constraints, we ensure our recommendations are tailored to achieve optimal performance and return on investment. This commitment to customization allows us to deliver the most effective solutions for producing consistently flat, high-quality steel, no matter the challenge. The first option we'll explore is the stretch leveler. This machine uses large amounts of hydraulic force to clamp the material and stretch it beyond its yield point. By doing so, it eliminates internal stresses, ensuring the material stays flat and stable through every subsequent process, whether it's cutting, forming, or fabricating. In simple terms, the stretch leveler grabs the material, stretches it, and locks in the flatness. It's one of the most reliable methods in the industry for producing flat-rolled products with consistent quality. To make this concept even clearer, we're about to watch a quick video of the stretch leveler in action. You'll see how our equipment transforms uneven material into perfectly leveled sheets with efficiency and precision. After the video, we'll dive into a case study involving a stretch leveler to gain a deeper understanding of the process in action. Let's look into a case study for the stretch leveler. Imagine a 50-foot stretch bed processing 40 KSI material. The beauty of this system is in its ability to tackle the material's elongation with precision. Let's break it down. For a material with a yield strain of 0.36%, we're looking at 0.816 inches of elongation for every 600 inches. But here's where it gets interesting. We typically target 3 yield strains, which adds up to 2.4 inches of elongation. After the material relaxes, we end up with a permanent elongation of about 1.6 inches. In simple terms, the material stretches more initially, 2.4 inches. But due to its elastic properties, it only remembers about 1.6 inches permanently after relaxation. So, what's the big takeaway? The key benefit here is that our stretch leveler affects the entire cross-section of the material all at once, producing steel that's truly memory-free. No more warping or spring back, just perfectly flat, stable material ready for whatever comes next. Now, let's dive into our most efficient and productive line, our temper mill cut-to-length systems, recognized as some of the most advanced and high-performing solutions in the industry. These lines use large rollers to compress the material, reducing its thickness slightly to reach the material's neutral axis, ensuring uniform thickness and length throughout the coil. To help visualize this, think of how you squeeze toothpaste from a tube. As the paste is pushed out, it elongates and creates a uniform, smooth layer. In the same way, the temper mill compresses the material as it passes through, producing consistent thickness across the entire sheet. The operator plays a critical role in adjusting the shape of the strip for the best results. The superior flatness and surface finish this process delivers are unmatched. It's especially ideal for products that require a high-quality finish for painting or other surface treatments. You can see this transformation in the video, where the material enters the mill with a dull gray finish and exits with a shiny, cold-rolled look. What makes this technology stand out is that it operates continuously without the need to stop the process. This results in more tons processed compared to other methods, making it the best option for high volume, high efficiency production. Lastly, let's talk about our roller levelers, which are the most commonly used machines for making steel flat. These machines evolved from flatteners, which are used across various metal processing lines to precondition the strip for further processing. However, a flattener alone isn't enough to meet the strict flatness standards the industry demands for flat sheets today. Both levelers and flatteners operate in a similar way. They use a series of rollers arranged in a pyramid configuration to bend the material up and down. The key difference is that levelers are typically equipped with more control points, like adjustable backup rolls, which allow for greater precision. Both types of machines work by bending the material and affecting the steel around its neutral axis, the zone in the middle of the strip where internal stresses are stored. Regardless of who designs or manufactures the machine, the neutral axis is always present. In the rest of this presentation, we'll dive into the details of how the neutral axis behaves and how it impacts flatness. We'll also cover the limitations of levelers and flatteners, explaining why these machines alone affect less of the material's cross-section compared to other processes. That being said, Delta Steel Technologies has made significant advancements in optimizing the roller leveling process, and we're excited to share more about these improvements throughout the presentation. Let's recap the three leveling methods we just covered. First, there's the stretch leveler. Think of this as our most straightforward approach. Straightforward in concept, that is. We use massive hydraulic force, we're talking millions of pounds, applied through grippers, to physically stretch the material beyond its yield point. It works on the entire cross-section of the material at once. The result? Truly memory-free steel, because we're elongating every fiber of that material uniformly. While it's simple in concept, it requires incredibly robust equipment to handle those forces. Next, we have the temper mill, which utilizes large diameter work rolls to compress the material. By slightly reducing the thickness, the material elongates, much like squeezing toothpaste from a tube. What sets this process apart is its triple benefit. It not only achieves superior flatness, but also neutralizes internal stresses within the material, ensuring a dimensionally stable and memory-free product. Additionally, the temper mill enhances the surface finish, making it ideal for painted or coated applications. This continuous operation, facilitated by Delta Steel Technologies' rotary shears, delivers high production rates with exceptional efficiency. Finally, we have the roller leveler, which is the most common method in the industry. This process uses a series of rollers arranged in a pyramid configuration to bend the material up and down, creating alternating tension and compression stress patterns through the material. For the remainder of our presentation, we'll focus on the roller leveler, as it's the most common method in the industry. Let's move forward and examine exactly how this process works. Let's dive into what happens when material passes through a roller leveler. As the material bends around the rollers, a complex interplay of forces happens. The outer fibers of the material, furthest from the roller, experience elongation, which puts them under high tensile strain. On the opposite side, the inner fibers closest to the roller undergo compression, experiencing high compressive strain. Right in the center of the material's thickness, we find what's called the neutral axis. Here, the material experiences minimal change, and this point is key to understanding how leveling works. Now let's move on to what happens when these forces exceed the material's yield strength. We enter the plastic deformation zone, where permanent changes occur to the material's shape. In contrast, areas where the stresses stay below the yield strength are in the elastic zone, meaning the material can return to its original shape once unloaded. In the next slides, we'll explore the neutral axis in more detail, which is crucial to understanding how steel behaves during leveling and key to achieving optimal flatness. It's important to understand a key concept that we'll be revisiting throughout this presentation: the neutral axis. This diagram represents the thickness of the steel strip we're processing. Here's the upper surface of the strip, and down here is the lower surface. In between, we have what's called the non-affected zone, or the neutral axis. This neutral axis is the area that hasn't been affected by the forces applied during the flattening process. It's where the steel's memory lives, meaning it holds residual stresses. Our goal with any flattening process is to reduce the size of this zone as much as possible. By minimizing the neutral axis, we can eliminate residual stresses and ensure the steel stays flat. Now, let's take a closer look at how the neutral axis changes as the flattening process progresses. As you can see in this diagram, the neutral axis has gotten smaller compared to the previous slide. This shrinking neutral axis is key to making sure the steel's internal stresses, or memory, are contained. As we apply forces to the strip, whether through stretching, bending, or compressing, the material begins to deform. The goal is to push the deformation further into the material, reducing the unaffected zone where those residual stresses are hiding. The smaller the neutral axis, the more we're able to control the steel's final shape. Here's our final view of the neutral axis, and as you can see, it's now even smaller. This is what we aim to achieve in every steel flattening process: a neutral axis that is as small as possible. At this point, the steel has undergone significant flattening, with the majority of its residual stresses eliminated. This means the steel's internal memory has been effectively erased, and the material will maintain its flatness through subsequent processes. Now that we know how the neutral axis is changing, let's explore how the material responds with each bend as it passes through the rollers, and how this continual process helps reduce the neutral axis even further. Over the next 5 slides, we'll follow the progression of a steel sheet through a 7-roll leveler, focusing on one bend at a time. Let's start with the first bend, marked in red with the letter A on our diagram. This initial bend has the deepest penetration and tightest curve of any point in the process. Here, we achieve maximum deformation as the material bends around the roll, with the outer fibers experiencing both compression and elongation, with an elastic zone in the center. As we move through the leveler, each successive bend will be progressively less severe. This gradual reduction in bend severity is intentional. It allows us to control the release of stresses we've introduced and achieve uniform flatness across the material. As we move to the next slide, pay close attention to both the size of the elastic zone and how the compressive and tensile strain shifts or alternates from side to side. These changes are important in understanding how the steel is worked as it progresses through each bend. This sequence is crucial for understanding how we achieve optimal leveling results. Now let's take a look at what happens in the second bend, the letter B in this case. At this point, the material reverses direction, but the bend isn't as deep as the first one, meaning there's less penetration. The top fibers are now being stretched, reaching about 2.5 yield strains, while the bottom fibers are being compressed to 2 yield strains. What's key here is that the elastic zone grows, creating a larger area that hasn't been permanently deformed. Also, an important detail is that the type of strain flips in this bend. What was compressive becomes tensile, and vice versa. This change, combined with the back and forth bending, helps relieve stresses in the material and stabilizes it for the following steps. Moving on to the third bend, letter C in red. This one is similar to the first bend, but with a key difference. The amount of strain is reduced. As the material passes through this bend, the process of elongation and compression continues, but it's not as intense as it was in the first bend. This gradual reduction in strain allows the steel to stabilize further, and the elastic zone continues to grow, giving us more control over the material's final flatness. This step plays an important role in refining the steel's structure and preparing it for the next stages. In the fourth bend, letter D, we're approaching the final stages of the leveling process. At this point, the material experiences very little actual plastic deformation. Most of the heavy lifting has already been done in the earlier bends, so here we're making only minor adjustments to the material. The goal is to ensure that any remaining stress is balanced out and the elastic zone continues to stabilize the steel. This stage helps fine-tune the flatness without putting too much strain on the material. Now, as we reach the final bend, letter E, it's important to note that the elastic zone, the area that isn't being permanently deformed, has grown significantly compared to our earlier bends. This growth tells us we're right where we want to be, with very little penetration at this stage. In fact, there's so little penetration that we're not introducing any further plastic deformation. At this point, the material is nearly fully leveled, and our main goal is to make sure the steel remains stable and flat. We're making the finishing touches here, ensuring that the internal stresses are fully balanced without pushing the material any further into permanent deformation. This allows us to deliver a flat, high-quality final product. Throughout the 7-roll leveling process, we go through 5 key bends, and at each one, we experience something called stack-up elongation. Every bend adds a little more elongation to the material. While each individual bend might only contribute a small change, the cumulative effect across all 5 bends is what helps us achieve the necessary flatness. These small increments add up, gradually relieving the stresses in the material and ensuring a flat, stable final product. It's this stacking of elongation spread across the 5 bends that makes the process effective. Now that we've walked through each individual bend and how stack-up elongation is accomplished, let's look at these 5 charts together. What we've just witnessed is the complete journey of our material through the leveler. Looking at these charts side by side, you can clearly see how the pattern of compression and elongation alternates with each successive bend. Notice how at the first bend, we start with that deep penetration, creating significant compression on top and elongation on the bottom. Then, as the material moves through each subsequent roll, these forces reverse. What was in compression now goes into tension, and vice versa. With each reversal, the magnitude of deformation decreases, and you can observe how the neutral region in the center gradually grows larger. As we move forward, we'll examine how different variables affect this pattern. We'll see how adjusting the roll penetration impacts material behavior, how the number of rolls in a leveler affects our results, and how different material properties, particularly yield strength, change the way we approach the leveling process. Understanding these relationships is crucial for achieving optimal flatness in your steel processing. On this slide, we're comparing 2 charts that illustrate the effect of plastic deformation on the material as it progresses through a 7-roll leveler. These charts highlight the relationship between the percentage of deformation and the amount of unyielded material. The first chart shows a material that has experienced 40% deformation. With this lower level of deformation, a significant 60% of the material remains in the unyielded zone, meaning the elastic zone is still large. This leaves much of the material's internal stresses unresolved, which limits the improvement in flatness. The second chart represents a case with 80% deformation. Here, the penetration is greater, and the unyielded zone is reduced to 20%. This means a larger portion of the material has undergone plastic deformation, permanently relieving residual stresses and achieving a much flatter and more stable result. The key takeaway is that increased deformation leads to a smaller elastic zone and greater material stability. By carefully controlling penetration and strain through the leveler, we can optimize the balance between deformation and flatness. The results demonstrate how achieving higher levels of plastic deformation, while maintaining precise control, produces a more consistent and flat product. Here we're comparing the performance of two levelers, one with 7 rolls and the other with 11 rolls, both operating at 50% plastic deformation. Let's focus on how the unyielded area, the portion of the material that remains in the elastic zone, behaves in each setup. The 7-roll leveler. With fewer rolls, the material experiences fewer bending cycles, meaning the penetration and strain at each bend are more concentrated. As a result, a larger unyielded area remains, indicating that more of the material stays within the elastic zone. While 50% plastic deformation is achieved, the fewer bending cycles limit how much of the cross-section is permanently altered. The 11-roll leveler. In contrast, this configuration introduces more bending cycles, distributing the deformation more evenly across the material. This reduces the unyielded area compared to the 7-roll leveler. The additional rolls allow for finer adjustments and ensure that a greater portion of the material reaches plastic deformation, resulting in improved flatness and reduced internal stresses. The key takeaway is that increasing the number of rolls allows for greater control over the deformation process, reducing the elastic zone and enhancing the material's overall stability and flatness. While both levelers can achieve 50% plastic deformation, the 11-roll leveler does so with better strain distribution and a smaller unyielded area, making it more effective for demanding applications. On this slide, we're comparing how different yield strengths affect material strain during the leveling process. We have two charts here, one showing 40 KSI material and the other showing 120 KSI material, both with 1-inch thickness. In both cases, the equipment is a 7-roll leveler, and we've maintained the same penetration, aiming for 80% plastic deformation. The key point here is that higher yield materials, like the 120 KSI steel, require more effort to achieve the same level of deformation. The strain is higher, and the material behaves differently under the same leveling conditions compared to the 40 KSI material. Despite using the same number of rolls and the same penetration settings, the higher yield steel resists deformation more, so it requires more force to reach the target. This comparison highlights the importance of adjusting the leveling process based on the material's yield strength. Stronger materials need more precise control and more powerful equipment to ensure we achieve the desired flatness without overworking the material. Now that we've explored the science and mechanics of how a roller leveler achieves flatness, it's important to understand the limitations of traditional leveling technology. Let's examine the key challenges operators face and the issues that can affect both product quality and operational efficiency. This understanding will be crucial as we move forward in our discussion. Let's take a closer look at some of the key limitations of traditional levelers. While they've been reliable for many years, they face several challenges that can impact both performance and efficiency. One major issue is that traditional levelers run all the rolls at equal speeds, no matter what material they're processing. This lack of flexibility means they can't adjust dynamically as the material elongates or changes during the leveling process. They also don't have dynamic torque adjustment, so the leveler can't fine-tune the force applied at each roll to match the material's needs. Another big limitation is the lack of tension control between the rolls. This can result in uneven leveling and less precise results. You'll also notice in the animation how elongation creates friction and bunching of the material between the rolls, which can cause slippage. This slippage increases wear on the machine and could lead to markings on the material, adding to more frequent maintenance and downtime. Lastly, traditional levelers don't allow for independent servicing on components. If one roll has an issue, it can impact the entire system, resulting in longer repair times and higher costs. Overall, while traditional levelers get the job done, these limitations can lead to inefficiencies, higher costs, and inconsistent results, especially when dealing with tougher materials or more complex applications. Now that we've identified the challenges, let's explore the solutions. On this slide, we'll take a closer look at torque limiting drives, which are commonly used in traditional levelers to manage strain on the rolls. While these systems offer some benefits, they also come with significant limitations. First, torque limiters provide reactive functionality, meaning they can't dynamically adjust when additional torque or speed is needed. Instead, they engage and disengage constantly to handle stress, which leads to wear and tear on the machine. This frequent engagement means the components need to be placed in an oil bath to minimize wear, increasing maintenance requirements. Additionally, these systems don't allow for independent control of each roll. If one roll needs an adjustment for better performance, the torque limiter can't accommodate it. There's also no independent servicing for components, meaning that if one part requires maintenance, it can affect the entire system. To illustrate these limitations, there's an article from Modern Metals magazine. The article documents how a company discovered an inherent flaw in this dated approach. They found their torque limiters were experiencing accelerated wear at the exit end of the leveler compared to the entry end, all because this half-measure solution does not avoid that all rolls turn at the same speed. This highlights one of the biggest challenges with torque limiters. All the rolls turn at the same speed, regardless of the material's change in needs throughout the leveling process. This creates uneven wear and reduces the effectiveness of the leveler. But don't worry, Delta Steel Technologies has developed more advanced solutions to address these issues and take leveling efficiency to the next level. Let me introduce you to Delta Steel Technologies' next-generation independent drive system for levelers. Working closely with customers, our engineering team has refined this technology into a proven solution that transforms the leveling process to maximize quality and efficiency. What makes our system unique is that each roll has its own independent drive, providing precise control of speed and applied torque. This innovation represents years of technological refinement, and the results have been remarkable. Here are the key advantages our customers are experiencing. Precise speed control. Each roll automatically adjusts to the exact speed needed, based on material behavior and the need to elongate through the leveling process. Second, proactive functionality. Our system adjusts to material changes in real time. Third advantage, improved leveling capability. The perfect amount of force and torque at the right time widens the leveler's capabilities. Our dynamic torque control algorithm applies torque on the fly to facilitate material elongation. Lastly, optimized material penetration. Field results prove that superior flatness is possible with less aggressive penetration while preserving material quality. In summary, the system orchestrates all elements of energy in perfect harmony to deliver force and torque to the strip, ensuring optimal material elongation. This technology represents Delta's commitment to innovation in metal processing. One of the great things about Delta's independent drive system is that you don't need to invest in a brand new machine to benefit from this technology. We can retrofit our independent drive system to your existing legacy levelers, regardless of brand or manufacturer, so you can enjoy the same precision, efficiency, and control without the need for a full replacement. By retrofitting your current equipment, you can boost performance with better speed and torque control, increase throughput and efficiency, extend the life of your current machine, save on costs and downtime by upgrading rather than replacing. This is a great way to modernize your operations. Take advantage of the latest technology and make the most out of your existing investment. Don't just take our word for it. Let's look at a real-world example of the impact our independent drive system can have on roll wear. One of our customers, a premier American steelmaker utilizing Delta Steel Technologies equipment, saw some incredible results after implementing our technology. They were able to double their cassette life, going from processing 300,000 tons to 633,000 tons. This means they experienced significantly less downtime, reduced maintenance costs, and overall improved efficiency. By extending the life of their equipment and minimizing the need for frequent repairs, This customer was able to keep their operations running smoother and more cost-effectively. It's a perfect example of how our independent drive system can make a tangible difference in the long-term performance of your equipment. Let's talk about parts and take a look at a comparison between a traditional single distribution box system and our independent drive system as it relates to spare parts. In a single distribution box setup, you need one large distribution box, along with one higher capacity motor, one large reducer, and one higher capacity drive. Each of these components comes with longer lead times and higher costs. If any one of these key parts fails, it can cause a significant delay and expense for repairs or replacements. Now compare that to our independent drive system where we use smaller reducers, motors, and drives for each role. Since each component is lower capacity, the price is much more affordable, and the lead times are significantly shorter. Plus, because the system is more modular, if one drive needs servicing, it doesn't affect the entire system, meaning you get less downtime and lower overall costs. In short, this system offers better efficiency, lower costs, and faster turnaround times for parts, making it a smarter long-term investment. As we near the end of our presentation, we'd like to share a short but powerful testimonial that brings everything we've discussed to life. You'll hear directly from Gary, whose facility has been running with our independent drive technology. In this brief video, Gary shares his review of the equipment. Let's hear him out.
My name is Gary Sutton, CTL lead, Ucore Tuscaloosa, and I just want to let you know, and whoever was involved in building our leveler, that is the best piece of equipment that we've put on this line ever.
We've covered a lot today, from understanding why steel doesn't come flat straight from the mill, to how we achieve precision leveling in your operations. While our focus today has been on steel, it's worth noting that these fundamental principles of material behavior apply to all metals. We hope this presentation has provided additional insights to your steel processing expertise and reinforced the principles behind achieving optimal flatness. At Delta Steel Technologies, we understand the complex challenges of steel processing. That's why we've developed comprehensive solutions extending beyond leveling equipment. Additionally to what has been mentioned, our portfolio also includes advanced cut-to-length lines, slitting lines, precision industrial knives, automation integrations, and upgrades. We also provide specialized services including maintenance, custom manufacturing, and equipment refurbishment. We kindly ask that you keep us in mind whenever you need these solutions. We're always here to help. Thank you for your time today. If you have any questions or would like more information, feel free to reach out. We're excited to continue the conversation and explore how Delta Steel Technologies can contribute to your company's success.